Okay, welcome to Chapter 6 review. We're going to be working with the gas laws and the heat curve. To work with these, you need to know how to convert. You need to know the pressure conversions here that I've got in red. You need to be able to compare, say, 6 atmospheres to 16 psi, which is bigger. You need to be able to know that these are standard conditions. So this is standard pressures. Anything bigger would be not standard, and less would be substandard. Now, you need to also realize if they ask you questions about real life, you can't go much higher pressure without causing damage, or lower pressure without causing damage to, like, the human body or to things. So make sure that you understand what's going on. Also know that if you increase pressure on a volume that can change, what's going to happen? Think of the marshmallows and the balloons that we did. If we increased the pressure, what happened? It got smaller. But the density within the balloon actually got more dense. As we made the vacuum and we made the balloon get large, the density inside the balloon became smaller. So you need to make sure that you're aware of that. You need to be able to convert Kelvin to Celsius and Celsius to Kelvin. Should be very simple and fast for you to do on your calculator. To get to Kelvin, just add 273.15. From Kelvin to get to Celsius, all you do is subtract 273.15. Now remember, with these pressure equilibriums here, you can set up fractions. For instance, if I needed to go from, say, 15 psi to millimeters mercury, I could easily do that by starting with the 15 psi, then setting up a factor or a fraction that was basically timesing it by 1 by taking the 14.7 psi, which would be equal to 760 millimeters mercury. Then I can quickly cancel out psi, times the 15 by the 760, divide it by 14.7, and get my answer in millimeters mercury. Whoops. Try that again. Millimeters mercury. I don't have a calculator here at home right now, or I'd throw that through for you. Basically, it should be about close to 770, 780, something like that. But you should be able to do that really quickly. You'll have your calculators with you, so no big deal. But you do need to know these standards, and you do need to know this temperature equation. Okay, so let's talk about the properties of the different states of matter. Remember density. Density is high with solid and liquid because we got as much as we can get in there. So to compress it, we can't really compress a solid or a liquid. Gases, however, are very compressible. So we don't want any gas, for instance, in our brake lines because we can compress it, and if we pressed on the brakes and the gas compressed and nothing happened to the calipers, that would be a bad thing. So gases can be compressed, but the liquid and solid cannot. The shape of a solid is definite. It has a specific shape. Liquids will take whatever the shape of the container is, and gases will also. Now if we look at the cohesive forces, this is what holds it together. Solids have a high cohesive force because they can hold their own shape. Liquids have a medium cohesive force. They're together, they're close, they have some kind of potential energy and particle attraction. That's why they're not in the gaseous state. Gases, however, have very low cohesive forces. Because they're so far apart, it's hard for the particles to attract each other. And all the potential energy is basically gone because it's now kinetic. Now, I ran out of room here down at the bottom, so I put in disruptive forces. Disruptive forces are the forces that result from particle motion. So as a solid, your disruptive forces would be low because you really don't have a lot of particle motion. As you get to a liquid, disruptive forces become a little bit higher. And as you get to a gas, disruptive forces are pretty high because they're moving like crazy. Okay, so have you ever gone and got a balloon and it's very high and flying, and then after a day it starts to not fly quite as high, and after another few days it falls to the ground, and pretty soon it's all shriveled up? Why does this happen? We put helium in the balloon, right? And helium should stay where it's put, right? Well, helium's pretty small. And so what actually happens are there little teeny holes in the balloon, and the helium comes out, and that's called effuses. So it goes through effusion through the itty bitty holes. Remember in the video we talked about effusion? So itty bitty holes for effusion, and then it diffuses through the room. So effusions through itty bitty hole, diffusions through the room. So it diffuses through the room once it becomes out of that little itty bitty hole, which is called effusion. So that's what happens is over time our balloons lose the helium to the outside. Okay, now we're on to the gas laws. Now you know how to convert between temperature and pressure, or we've been reminded how to do that. Now you need to get onto the gas laws. Remember, ideally you're not a pervert. PV equals nRT. Remember the constant R. Don't forget, you probably want that on your 3x5 card along with the conversions we talked about earlier. 0.0821 atmospheres times liters divided by mole times degrees Kelvin. Need to be able to do that. Now you want to be able to rearrange this equation, remember, and set it equal to R. So R is going to be equal to PV divided by RT, or NT, sorry. That's going to be able to be set equal to another PV divided by NT. And we can put 1s on the first set, and we can put 2s on the second, and this is known as the combined gas law. Now from the combined gas law you can get all the rest, but you got the combined gas law from the ideal. Remember that you can hold any of those things constant: volume, moles, temperature, pressure. And in the combined gas law they don't have to be in a specific unit, unlike the ideal gas law. They have to be in the ideal gas law, they have to be in these units right here. Where the combined, they just have to be the same unit. So pressure on one side has to be the same unit as pressure on the other side. Temperature always, though. Temperature always has to be in Kelvin. Okay, so remember that. Temperature always has to be in Kelvin for the gas laws. That's because if it's not in Kelvin, it could be a 0 on the bottom, and you divide anything by 0, and it becomes undefined. Okay, so from this we get several other laws. We can also get Boyle's law, Charles' law, Gay-Lussac's, and Avogadro's. Remember the little tricks I told you? Boyle's, temperature's held constant. Most times moles will drop out, which is the N. So we sort of ignore them except for Avogadro's. So Boyle's had temperature constant, so it drops out. Charles holds pressure constant, so it drops out. Gay-Lussac holds volume constant because it sucks. Remember Prince Charles is under constant pressure, and Boyle is when the temperature boils. Avogadro's, there's no rhyme or reason. You just got to remember pressure and temperature were held constant. So these give you the main ones. Now remember my little trick so that you can do a lot of other things with it, which was PTV. If you want to know what's happening to a system and you're holding one of these constant, pressure, temperature, or volume, put your finger on whatever you're holding constant. For instance, if pressure is held constant and you are increasing volume, then you'll tilt it this way, and so if volume goes up, temperature is going to go up because you're holding constant at the P. I hope you remember that. If not, come talk to me and I'll go over it more. Okay, remember there's two other laws. Dalton's delta law, which is the pressure total is equal to all the little parts added up, all the little pressures added up. And we will have done some examples of this in class, so hopefully it'll be pretty easy. We also did that lab where we captured the gas through the water, and we actually used this rearranged. So the pressure of the gas is equal to the pressure total minus the pressure of the water. And that's how we use it oftentimes in lab. Now Graham's law was the rate of A divided by the rate of B equals the square root of the molecular mass of B divided by the molecular mass of A. Remember I called this Grandma's law. We did the experiment in class where we did the straw and we put ammonia on one side and we put hydrochloric acid in the other side and we got the white ring of ammonium chloride. This is the same thing. Now if they say relative rate, this whole thing together is a relative rate. So if they give you one number and say it's the relative rate, that's that whole thing together. Make sure on this one, the trick on this one is the first one you come to is A, the second one you come to is B. Make sure that you flip the molecular mass, because notice the A and the B are flipped. So those are the things you need to watch. We will have practiced a whole bunch of these in class, hopefully. You'll have got it. It's not real hard. It's mostly plug and chug. I think the hardest thing for most kids in these gas laws is just identifying each thing in the stem of the question. So as you get to something, label it volume. If you get to a second volume, then go back and label the first one V1 and the second one V2. So make sure you identify what you've got. And we will have done this in class and identified them, so hopefully this will be fairly easy. Do remember again to make sure that your temperature is in Kelvin while you're doing the problem. And be careful, because a lot of times they will ask at what degrees Celsius something is. So do the problem in Kelvin, then change back to Celsius. So take your Celsius degrees, change to Kelvin, work the problem in the gas law, then change back to Kelvin. You cannot do the gas laws in Celsius. I can't stress that enough. That is the biggest mistake I see there, okay? Okay, so you can do stoichiometry of gases given an equation and say that I started with 6 moles of O2 and I wanted to find out how many liters of water that I was going to produce. In order to do this, I'm going to set up just like I would in regular stoichiometry. I would start with the 6 moles of O2. Now the important thing here is that you need to know that it is at STP, or standard temperature and pressure. If it's not, you cannot use the stoichiometry method. You've got to go use PERV-NERT or the combined gas law, one of the two, or a version thereof, to get it into standard. So we would start with 6 moles of O2. We would use the ratio here for every 1 mole of oxygen, there are 2 moles of water. Then we knew that moles of water would cancel out. Our next conversion to get it into liters would be using our mole map going straight up. So for every 1 mole of H2O, there are 22.4 liters of H2O. And crossing out moles of H2O, we would be able to, and this is part of Avogadro's law, knowing that at standard conditions there's 22.4 liters of any gas for every 1 mole of that gas. We would be able to take and times that through and be able to get liters of H2O. Again, I forgot my calculator at school, so you would just times that through and get your answer. Okay, we've got 2 basic heat curves that we're worried about, but from both of them we can understand a bunch of things. The one at the top of the chart here basically takes us from a solid right here, heating a solid, melting or freezing the solid to a liquid. The liquid is right here on this area, and then boiling or condensing, and then gases up here at the far right. We know as we get higher on this chart, the temperature increases. We know that as we move to the right, energy is added. That's known as endothermic. I'm putting energy in. As I move to the left, as the blue shows, then I'm taking energy out. So if I'm condensing, I'm taking energy out of the gas. If I'm freezing, I'm taking energy out. That's known as exothermic. you need to be able to identify what's happening, is energy being added, and is it endo or exothermic. Now down here at the bottom we've got a phase diagram, and we need to be able to know the words that represent the phase changes. Most of us know melting and freezing and boiling and condensing, but we need to know sublimation and deposition. The reds here are when we are putting energy in. Okay, they're endothermic. I have to put energy in to melt or boil or cause sublimation. I have to take out energy where the blue is concerned here, deposition, freezing, or condensing. So I need to be able to know which are exothermic and which are endothermic, and I need to know the phrases of each. I also need to know when temperature is decreased, what happens to the different states. Remember, as I go to the left, on the top diagram, I'm decreasing temperature because my line is coming down. And also on the bottom diagram, as I go to the left, I'm also decreasing temperature. Now remember the other things on this diagram down here at the bottom. If I have 1 atmosphere being right here, and I go across and I hit this line, that becomes my normal freezing point, what we consider our normal freezing point. And I come around to hit this line, that's my normal boiling point. These are when the vapor pressure is equal to the boiling point for the normal boiling point is at 1 atmosphere. So for instance, if I go up to a higher elevation, my atmospheric pressure decreases. So because my atmospheric pressure decreases, then you look at the boiling line, the boiling point will actually go down. So if you're a backpacker or an avid hiker and you go up to the mountains and you want to cook noodles, it's probably not a good idea because the pressure's lower up there. You'll actually end up getting soggy noodles, which isn't so yummy to eat. They have special backpacking things because of that, because water boils at a lower temperature and it just makes the noodles soggy. Okay, so higher elevation than 1 atmosphere decreases the boiling point of the liquid. Okay, so hopefully you can think of things as you're reading it, what happens. Now, with the vapor pressure of liquids, you need to also make sure that you take into account the polarity of a liquid. If a liquid is extremely polar, it's going to stay in a solid and liquid longer than and go to a gas last. The temperature of the liquid also takes into effect and how fat these molecules are. Just think of our experiment when we did Graham's law. The slower molecules were the bigger molecules. So they don't like to go into vapor as readily as smaller molecules do. Okay, so we need to be able to find the heat of fusion and the heat of vaporization. Usually, they're usually just trying to find Q. And Q for this basically is just the heat of fusion, and Q is just the amount of heat. So the heat of fusion times the mass or mole, depending on, I'm going to put mole mass down here, depending on what you're given. If your heat of fusion is given in joules or calories per gram, then you use the mass. You times it by the mass. If it's given in calories per mole, then you got to change it to moles first. Most of the time they're going to do mass for you. It makes it just a little bit easier, but you should be able to do both. Same thing with heat of vaporization. It's just the amount of heat taken to vaporize liquid or condense liquid. So here we just take the amount, the unit they gave us for HVAP, and we would times it by, out this time I'll put mass on top, or mole, depending on what HVAP was given in. Not too hard to find Q. All you got to do is times the two together. Not a big deal. Now, for our heat curve, those were the flat parts. So the heat of fusion was the flat part where it was melting ice or melting the solid, and heat of vaporization was the flat part where it was changing liquid to steam. We also have just the regular heat, which was the mass times the specific heat times the change in temperature. We use this in lab. This is a point at which you're heating a solid or you're heating a liquid. That's how much energy it takes. So you need to be able to throw in to any of these three equations and get an answer. But you need to know which one you've got. Now on this one, you don't have to have it in Kelvin. If you put it in Kelvin, it's not a big deal because the difference in Celsius and Kelvin are going to be the same. So just heads up. Remember that CP is specific heat. So you might be given that, or you might be asked to solve for that. And this, of course, Q is just the heat. Remember that the effect of changing altitudes on boiling point is that the higher I go in altitude, the lower the boiling point becomes. The lower I go in altitude, the higher the boiling point becomes. So just remember that little thing. Remember looking at the physical states. Solid has the lowest energy, and it increases to where you're a gas that has very high energy. Okay, you're up to it now. Study your gas laws and see your heat curves. Get your 3x5 card ready, and let's ace this test.